let's have a look at some applications of magnetic and electric fields and the effect on individual moving charges. First of all, cross electric and magnetic fields. So if we have a magnetic field acting in one direction and an electric field acting in the opposite direction, we can arrange a magnetic field and the electric fields perpendicular to each other in order to have an effect on the moving charge so that it stays within a straight line. We should remember that a charge within an electric field is always going to experience a curve. So if we had an electric field here, positively charged on one side, negatively charged on the other, a negative charge entering that field is going to go towards, and then it's going to be attracted towards the positive and repelled from the negative. We don't necessarily want the charge to do that. We may want the charge to move in one straight line. So we need to provide a deflection, and that deflection is provided by a magnetic field. This is the basis of particle accelerators. So we cross the fields. We have a magnetic field acting in one direction and an electric field acting perpendicular to that direction. Now this arrangement is called a velocity selector, and it's used as part of larger systems where the properties of the charged particles are being measured. So we tend to use this in a large system like a particle accelerator, where we want to have a look at the properties of the individual particles. Now, when we say the properties of the particles, what we're really talking about is the magnitude of their charge and the magnitude of their mass. Within a particle accelerator, most often we're aware of the magnitude of the mass and the magnitude of the charge. However, when the particles are colliding with each other, we can use the velocity selector in order to help determine the mass and the charges of the components that are produced, the products of the particle acceleration smashing together. So let's have a look a little bit more into the velocity selector. Again, here is the same diagram that we had, and you should be able to describe this. So in this diagram, the magnetic field direction is into the page. We can tell that from the crosses. A positive ion is fired from the source into the cross magnetic field and electric field as shown within the diagram. So the magnetic force acting on this using the right-hand rule you'd find is upwards. And we can determine the size, the magnitude of that force using the equation F equals QVB. The electric force is acting downwards because I have a positive particle is going to be repelled by the positive plate, which is on the top, and attracted to the negative plate. So I have a downwards force due to the electric field, which has a value of QE, and an upwards force due to the magnetic field, which is QVB. Now, if this particle is moving in a straight line, that must mean that the upwards force from the magnetic field is equal to the electric force from the electric field. So when those forces are balanced, QVB is equal to QE, which of course we can then rearrange because we can take out the common value of the charge and say V is equal to E over B. The velocity of the particle is equal to the size of the electric field, the potential, divided by that of the magnetic field. So E is the electric field strength in newtons per coulomb, B is the magnetic induction in newtons per ampere per meter, or Teslas, obviously. Now, dependent on the size of the electric field and the magnetic field, only certain ions with one specific velocity will follow the undeflected path. So if I've got a particle of the correct velocity, it will follow one straight line path. If it doesn't have the correct velocity, it's going to be deflected in a certain way. The direction of the deflection depends on the velocity of the charge. If my charge is moving at a different velocity, that would allow us to determine what kind of charge it is. So think about it in terms of momentum. If I know the size of the electric field and I know the size of the magnetic induction, and then I find the velocity of the charge. If I know the velocity of the charge, and in other ways finding the mass of the charge, then I can determine its momentum. If I can determine its momentum, I can also determine its kinetic energy. And this is kind of how we found out about beta decay. So beta decay and the fundamental particles, the leptons, we found by experimentation that when a neutron broke down to form a proton and an electron, there was some additional energy unaccounted for, because when we used the conservation of linear momentum, there was something missing. That missing momentum was determined using a velocity selector, and that gave us evidence for the existence of leptons, which are subatomic particles. So what we need to take note of within the equation V is equal to E over B is that this equation is independent of the mass of the charge. It's independent of the charge, of the ions. It's only the velocity of that which determines whether they'll be undeflected as they pass through cross fields. So to explain that further, let's have a look at an example. Example for the velocity selector. Here's our velocity selector diagram again. Protons, positive charges, are fired from the source into the magnetic field, and that magnetic field is perpendicular to the electric field applied, as shown in the diagram. Magnetic induction is measured as being 115 milliteslas. Remember, small numbers of teslas. We'll need to do a conversion later on. And we are told that there's a potential difference of 2.50 kilovolts across the plates. The place separation is 0.1 meters. Here are your questions. Calculate the electric field strength between the plates. So E, how do we work that out? E equals QV. So you're going to need to know what the charge on a proton is for this. Calculate the force on the proton due to electric field. F equals ILB. Determine the speed of the proton as it passes through the apparatus undeflected. QV, that's the electric field, is equal to a half mv squared. So you're going to need to know the mass of the proton. An alpha particle, remember an alpha particle is made up of 2 protons, 2 neutrons, is fired into the cross fields. It has twice the charge and 4 times the mass of the proton. State the velocity it must have to pass undeflected through the fields. You must justify your answer. You're looking at the ratio of the electric field to the magnetic field. So how did you work out the electric field before? What's changed about that? Pause the video, have a shot at the question. Okay, hopefully you've had a chance. Here we have a look just in numerical solutions. So E is equal to V over D, which is 2,500 divided by 0.1, which gives us 25,000 volts per meter. F is equal to QE. V is equal to E over B. And our value of our velocity is 2.17 times 10 to the 5 meters per second. Because remember, the undeflected path is independent of mass or charge. So the same velocity we got for part B is going to be for part C. So let's have a look at an example of this mass spectrometer, just for interest only, because this is not specifically part of the course. We can see in the diagram here that the magnetic field is coming towards us. That's the circles with the dots in the center. So a mass spectrometer is used to determine the range of atomic masses of ions of a particular element. and that will tell us what the composition of a certain material, and we can compare that against known compositions of other materials in order to find the material that we are examining. So this is used a lot, for example, within forensic science. Ions of the same charge and of one particular velocity will pass undeflected through the first part of the apparatus. That's the velocity selector part. Then, when they enter the magnetic field, they're going to follow a circular path due to the nature of the charge. The radius of the circular path depends on the mass of the ions. The detectors can measure the relative abundance of different isotopes, different masses of the element, and then we can use the relationship. We're just relating F QVB, that's the force due to the magnetic field, to our central force, mv squared over r. Rearranging this, we get a value for the equation. R, the radius, is equal to mv over bq. So the radius of the deflection will depend on the mass of the particular isotope, will depend on the velocity of the isotope, and obviously the charge and the magnetic field, which we can previously measure. Another example is looking at the charge to mass ratio of an electron. The charge to mass ratio of an electron was first discovered by J.J. Thomson in 1897. Now you may remember J.J. Thomson, because J.J. Thomson was also credited with the discovery of the electron and won the Nobel Prize. So here we have a deflection chamber, a teletron tube, and so electrons are steered in a circular path by a magnetic field. The central force is provided by the magnetoforces, and as with the previous example, the mass spectrometer, we are looking at QVB, the force due to the magnetic field, being equal to the central force acting on the particle. Therefore, Q over m, the charge to mass ratio, is equal to the velocity divided by the magnetic induction and the radius as a product. So for an example, if we have an electron entering a magnetic field of velocity of 4.2 times 10 to the 7 meters per second, and the magnetic induction is 9.3 times 10 to the 4 Teslas, the radius of the electron path is measured as 0.26 meters, you can calculate the charge to mass ratio. Have a shot of that, pause the video. You should have ended up with a value of 1.74 times 10 to the 11 coulombs per kilogram. Now the importance of the charge to mass ratio is that if we have different particles with the same charge to mass ratio, that means that they are going to move in the same path within the vacuum when subjected to the same electric and magnetic fields. And the charge to mass ratio of an electron allowed us to accurately determine the value of the mass of an electron. Another interesting point is that the ratio of the charge to mass, the coulombs per kilogram, in some ways is also known as the Thomson in favor of J.J. Thomson.